derivatives. Section 2.1, derivatives and rates of change. On the very first day, we gave an intuitive concept of what the derivative is. We'll start out with some intuitive concepts of the derivative. And now that we have the concept of a limit, we'll be able to give a more rigorous definition of what we mean by the derivative. So first, tangent line. The tangent line to the curve y equal f of x at the point a, f of a, is the line through the point P with slope m equaling the limit as x approaches a of the following difference quotient, f of x minus f of a over x minus a, provided that this limit exists. So suppose we have some curve relative to some coordinate system at some point A, then the line that best approximates this curve near x equal a will be called the tangent line. So as we get closer, closer and closer and closer to x equal a, then my y values, then my line here, my curve looks more and more just like a line. Whatever that line is that it looks like will be called the tangent line. The tangent line to y equal f of x at x equal a is the best linear approximation to y equal f of x at x equal a with slope, and we'll denote the slope here with f, the little prime on top, the little dash on top, at a, equaling the limit as x approaches a of the difference quotient, f of x minus f of a over x minus a. So suppose I have some function relative to some coordinate system near x equal a. Let the tangent line be the best linear approximation. So m equaling f prime at a is the slope of the tangent line to f of x at x equal a. It is the best linear approximation to y equal f of x at x equal a. The slope of the tangent line is denoted by f prime at a. We will calculate this slope using slopes of secant lines. So we can't really figure out the slope at one point, but I can find the slope at 2 points, the change in y over the change in x. So I will look at a secant line. A secant line is, well, suppose I have some function, y equal f of x, relative to some coordinate system. Then if I look at 2 points on the line, on the curve, the line passing through these 2 points is called the secant line. And so a secant line just is a line passing through 2 points on the curve. Well, suppose the 2 points are as follows. A, f of a, and a plus h, f of a plus h. So I'm just going to look at the value of f when x is a and when x is a plus h. Then if I let h get smaller and smaller, so I keep approaching a, then the slopes of each of these secant lines should approach the slope of the tangent line. So as h approaches 0, the secant lines should approach the tangent lines. So the slopes of the secant lines should approach the slope of the tangent line. So I'm going to approximate my tangent line by looking at a whole bunch of secant lines. Well, I know what the slope is of a line through 2 points. So m equals y2 minus y1 over x2 minus x1. Well, if I look up here, I have a y2 minus y1 over x2 minus x1. The slope is the change in y, f of a plus h minus f of a over the change in x, a plus h minus a. Well, the a's cancel. So this is equal to f of a plus h minus f of a divided by h. This is called the difference quotient. It is just the slope of the secant line. I will denote by f prime the following limit. So f prime at a is defined as the limit as x approaches a. I'm sorry, let's start all over again. I said it wrong. F prime at a is the limit as h approaches 0 of f of a plus h minus f of a divided by h. Let's look at the same idea, but involving velocities. So let s equal f of t be the position function. Then the average velocity from t equaling a to t equaling a plus h is f of a plus h minus f of a divided by h. This should look familiar. The instantaneous velocity at a is denoted by v of a. The limit as h approaches 0 of f of a plus h minus f of a, all divided by h. Same as above. The tangent line to y equal f of x at a f of a is a line through a f of a where the slope is equal to f prime at a, the derivative of f at a. Rates of change. The change in x, sometimes called the increment of x, is delta x, x2 minus x1. The change in y is delta y, f of 2, f at x of 2 minus f of x of 1. The average rate of change of y with respect to x over the interval, closed interval from x1 to x2, is the slope of the secant line through the point x1, f of x1, and x2, f of x2. It is the difference quotient. Delta x over delta y is equal to f of x2 minus f of x1 divided by x2 minus x1. The instantaneous rate of change, well, just make this go to 0. Of y with respect to x equaling x1 is the slope of the tangent line to the curve f of x at x1 comma f of x1 is the limit as delta x approaches 0 of delta x over delta y over delta x is the limit as x2 approaches x1 of f of x2 minus f of x1 divided by x2 minus x1 is the limit as h approaches 0 of f of x1 plus h minus f of x1 over h. The derivative of a function f at a is f prime at a is equal to limit as h approaches 0 of f of a plus h minus f of a over h. Provided, of course, that the limit exists. F prime is equal to the limit as x approaches a of f of x minus f of a divided by x minus a. These are all just saying the same thing. The tangent line to y equal f of x at a f of a is the line through a f of a, whose slope is equal to f prime at a. The derivative of f at a, since I know the slope of a tangent line, the derivative of f at a, and I know a point on the line, then I can use the point slope form for the equation of a line to find the equation of my tangent line. Y minus f of a is equal to f prime at a times x minus a. Or in other words, that y is equal to f of a plus f prime at a times x minus a. The derivative, f prime at a, is the instantaneous rate of change of y equal f of x with respect to x when x is equal to a. Some terminology. Whenever you see the term marginal, think of derivative. Whenever you see the word instantaneous, think of derivative. So the marginal revenue is the derivative of the revenue function. The marginal cost is the derivative of the cost function. The marginal profit is the derivative of the profit function. Again, when you say instantaneous, think of derivative. So instantaneous velocity is the derivative of the velocity, the derivative of the position function. So whenever you say instantaneous, take the derivative. Whenever we say marginal, take the derivative. If we say average, you don't take the derivative. It's the slope of your secant line. It is the difference quotient. Oh, so let's do some examples. On page 113, in problems 5 through 8, find the equation of the tangent line to the curve at the given point. So problem number 8. I want to find the equation of the tangent line to y equal 2x plus 1 over x plus 2 at the point 1, 1. So first, let's try to find the slope of the tangent line. So I have a point. If I know that I have a point on the line, if I knew the slope of the line, then I could find its equation. So let's try to find the slope of the tangent line. Well, the slope of the tangent line at x equal a, at x equal 1, is just f prime at 1. So how do I find a tangent line? Well, we did this limit of a whole bunch of secant lines. So let's find the slope of the limits of secant lines. the slope of the limit. Well, of difference quotients. Each of these difference quotients are just found as slopes of secant lines. So let's do that. So f prime at 1 will equal the limit. Maybe I'll use, so I gave you actually 2 or 3 equivalent forms. I guess I'll use this form. Not that it really matters. I'll let x approach 1. And so I'll find the slope through the point x, f of x, and through the point 1, f of 1. So this will be f of x minus f of 1 over x minus 1. So this will equal the limit as x approaches 1 of, well, f of x, which is 2x plus 1 over x plus 2. And f of 1 is 1. So f of 1 is 1 because that's what it tells us. Also, you could just plug in 1. You could also plug in 1 here. Maybe I should do that also. So let's plug in 1. That's a 2 plus 1 is 3. 1 plus 2 is 3. 3 divided by 3 is indeed 1. So yes, I verified it. But I could also just look. Well, I guess I should verify it because if not, I would be in trouble if f at 1 was not equal to 1. I couldn't do that this problem. Okay, so minus 1 over x minus 1. So let me try to simplify this. So first, let me get rid of all my denominators. So let me multiply and divide by x plus 2. So this is equal to limit as x approaches 1. The x plus 2's cancel, so I get a 2x plus 1 minus x plus 2 over x squared plus 2x minus x minus 2. Multiplying, so I get x squared plus 2x minus x minus 2. Okay, which I could have done up here also. Maybe I will do that up here. Maybe I'll do that also up here. Oops. So the x plus 2 cancels here. Next, x times negative 1 is negative x. And 2 times negative 1 is negative 2. So this is minus x minus 2. And let's simplify that. So this is limit as x approaches 1. So 2x minus x is x. 1 minus 2 is negative 1 over x squared. 2x minus x is x minus 2. So this is the limit as x approaches 1 of x minus 1 over. I can factor the denominator. I can factor this as x minus 1. Oops. I can factor this as x minus 1, well, x plus 2 times x minus 1. And so the x minus 1's cancel. And so this is equal to limit as x approaches 1 of 1 over x plus 2, which is equal to 1/3. Okay, so therefore, the slope of my tangent line is 1/3, and the point on the tangent line, well, was given as 1, 1. Therefore, the equation of the tangent line of the tangent line to y equal f of x at 0.11 is, well, again, I have a point and a slope, so I'll use the point slope form for the equation of a line. So y minus y1 equaling m times x minus x1. And that's the equation of my line. So I've used the, that's the equation of my tangent line. So I've used the point slope form for the equation of a line. Which was y minus y1 equals m x minus x1. Okay. Any questions about that? Okay. So let's do problem 31 through 36. Find f prime at A. What's A? Okay. It doesn't tell you what A is. Okay, so it's just find f prime at A, doesn't give you A. Problem 36. So I guess I'll have to do this for all A. So f prime, so find f prime at A. Problem 36, f of x is equal to 4 over the square root of 1 minus x. So first, let's figure out the domain of f. Well, let's figure out the domain of f prime. Note the following. So note the following. So I have that f prime at A, let's say, is equal to limit as x, yeah, let's do that. X approaches A of f of x minus f of A over x minus A. So first thing to notice is that if A is in the domain of f prime, it has to certainly be in the domain of f because f of A has to be defined. And so no matter what, we must have that the domain of f prime is smaller than or equal to, it could be equal, of course, than the domain of f. So first, let's find the domain of f. Then we can figure out what the domain is of f prime. So the domain of f. Let's figure that out first. I don't want to divide by 0, nor do I want to take the square root of a negative number. So I want that whatever is inside a square root is positive. So I want that 1 minus x is greater than 0. add x to both sides of your inequality. And so I have here that x is less than 1. So the domain of f is negative infinity to 1. So let's first look what happens if A is in the domain of F. Okay, so let A be greater than be less than 1. So then we can actually do this. So then f prime at A is equal to. Last time we did it where we did the limit as x approaches A. Let me do the difference quotient where I use h's. Why? I don't know why. Because it's a variety. So I'll use this definition of the derivative. They're all, so far, everything that I've given so far are all equivalent definitions, and none of which will really be any easier than the other. And so I'll use a variety. So the limit as h approaches 0 of f of a plus h minus f of a all divided by h. Okay, so f, oh, I guess I need a little bit more room here. So let's take the limit as h approaches 0 of f was 4 over the square root. So 4 over the square root of 1 minus x, so a plus h, minus 4 f of a, and again, f of x was 4 over the square root of 1 minus x. So this is 4 over the square root of 1 minus a. Let me try to simplify this. So if I try to simplify this, let me try to somehow get rid of the denominators. And so let me multiply by least common denominator, which is the square root of 1 minus a minus h and the square root of 1 minus a. Just simplifying the denominator here, changing all the signs inside the parentheses. And so 1 minus a minus h and 1 minus a. Okay, so this is equal to limit as h approaches 0. Let me write down the gigantic denominator. So this is h square root of 1 minus a minus h times 1 minus a. So first off, well, this is going to cancel with this. So I just have these multiplying each other. And so I just have 4 times radical 1 minus a. Next, the radical 1 minus a's cancel. So all I have remaining is the minus 4 times radical 1 minus a minus h. Now, I want to get rid of the square roots. So this is equal to limit as h approaches 0. Let me factor out the 4 first, so it looks a little nicer. 1 minus a radical minus 1 minus a minus h radical over h 1 minus a minus h radical 1 minus a radical. So let's try to get rid of the square roots. I'll multiply by its conjugate to get rid of the square roots. And so let's multiply and divide by radical 1 minus a plus radical 1 minus a minus h. And divide by the same thing. 1 minus a radical plus 1 minus a minus h radical. Okay, so this is equal to limit as h approaches 0 of 4 times the 1 minus a's cancel, the radicals cancel, so I just get 1 minus a. The radicals cancel, so I just get a negative times the quantity 1 minus a minus h. So the minuses cancel. The minuses will change all the signs inside. So I get a minus 1 plus a plus h over gigantic stuff. H 1 minus a minus h radical 1 minus a radical times 1 minus a radical plus 1 minus a minus h radical. Okay, good. So some things are going to cancel. And so ones cancel, a's cancel. So this is equal to limit as h approaches 0 of 4h over lots of stuff in the denominator. H 1 minus a minus h 1 minus a 1 minus a 1 minus a minus h. Okay, h's cancel. And so this is equal to limit as h approaches 0 of 4 over 1 minus a minus h 1 minus a 1 minus a 1 minus a minus h. Okay, so notice that, well, up until now, if I would have plugged in h equaling 0, I would have gotten a 0 over 0. I have a 0. Here I have a 0 over 0. Still I have here a 0 over 0. Here I still have a 0 over 0. But now if I plug in h equals 0, I get 4 over rad a minus 1 times rad a minus 1 is, I'm sorry, rad 1 minus a times rad 1 minus a is 1 minus a. rad 1 minus a plus another rad 1 minus a is 2 rad 1 minus a. So the 2's are going to, the 2 and the 4 will simplify. And the 1 minus a and the radical 1 minus a's will simplify. So this will become, maybe I'll write it this way. So this will become 2 over 1 minus a to the 3/2, which I could write as 2 1 minus a to the negative 3/2. Okay, good. So this implies the following: that f prime at a is equal to 2 times 1 minus a to the negative 3/2 if a is less than 1. And it doesn't exist if a is greater than or equal to 1. Okay. So in this particular case, the domain of f prime is negative infinity to 1.
Wait, why does it not exist at a 1?
Oh, why doesn't it exist at 1? Well, let's see. Let's look here. Plug in 1, what happens?
Yeah, okay.
Yeah. So you're dividing by 0. And if a is bigger than 1, then you're taking the square root of the negative number. So that's why, obviously, you don't want to divide by 0. You don't want to take square roots of negative numbers.